Thanks very much for the invitation. It's great to be here. At the moment, I work in two sort of different research domains. I'm a cryptographer in my research at Columbia University. I've also worked as a code breaker. I also do some machine learning for a stock exchange in the US called IEX. And most of my job there is building models that detect violations from the intention of fair access in our market. So we've tried to design a market that doesn't privilege certain kind of high-frequency participants. And I build models that are responsible for sort of ensuring those kind of policies that we've put into place. So a lot of the code that I write and design and the algorithms I work on are intended to be out in the wild in places where there's highly incentivized efforts to sort of steal the secret keys underlying those cryptographic systems and or subvert the intentions of the algorithm design. So in my head, when I'm designing algorithms, sort of always an army of people on the other side trying to violate the properties that we're trying to build into the algorithm. So it's a bit of a different design model, perhaps, than I started out with as a mathematician when I learned the paradigm of functions, and we sort of didn't even think about how things are actually computed in the algorithmic sense. So I want to take you through a bit of my process of thinking in this. And as a mathematician coming to this, it comes from the understanding of code as being very simple building blocks. So we start with the algorithm as a sequence of small little steps where we understand individual steps in pseudocode, like writing to memory, reading from memory, doing some basic algorithmic operations and conditionals. And we sort of get a little bit fancier. We maybe get randomized code. We maybe get more complicated branching instructions and conditionals, and we sort of build algorithms out of this. And eventually we get things that sort of look complex, but are really made up of these individual simple building blocks and instructions. And we reach a point of mastery where we can do lots of fancy looking things, and we could build lots of complicated algorithms. And then even beyond that, we start to build algorithms about designing algorithms, which is kind of what machine learning is, and building layers of abstraction and layers of recursion on top of these things. But sometimes it is only in the violations of our core and underlying assumptions that we really understand simultaneously both the beauty and the limitations of the building blocks that we're using as part of this design process. And we have to have abstractions in order to make progress, in order to get to this point of mastery where we can do these complicated things. But at the same time, in cybersecurity, what we're seeing is that built into our abstractions are sort of the seeds of our destruction, and these implicit assumptions that they make that we've internalized so far now that we really aren't prepared for their violations in practice. And so the way that this sort of plays out in the cybersecurity research world is we have this process of bottom-up knowledge generation from simple components up to higher and higher level abstractions that build upon the implicit assumptions of the layer before. And when these things get sort of turned on their head, we have sort of top-down knowledge generation of, oh, we now need to incorporate this new reality into our design of systems and into the model, and we sort of go back to the drawing board and build building blocks. And I think it's helpful to remember that this is sort of the process, because those same underlying abstractions and building blocks that we've inherited from the generation of scientists before, we're also sort of driven by this process, and we're modified to meet the needs and the realities of computing and mathematics at that time, and didn't really arise from necessarily fundamental principles, but they sort of fit the model at the time. And there's a saying we have in both statistics and in every other area of math that all models are wrong, but some models are useful. Well, some of the models we have in algorithms now are starting to be wrong in ways in practice that are violating more of their intention than we realized before. And so we often like to think of knowledge as evolving like this, and if we paint cybersecurity in this kind of picture, we imagine that defenses will sort of evolve along with algorithm design, but it actually looks something a little bit more like this, that sometimes we have to take a step back in order to take a step forward. So I want to talk with you today about some of the examples of sort of core principles that we think of when we think about algorithms that are sometimes violated in practice, and sort of how that shakes out in terms of thinking about security properties of the algorithms that we're trying to design. And really, when I was taught about algorithms, I was taught about certain abstractions that we sort of enshrine in the way we write pseudocode and in the way we analyze algorithms And there are some implicit assumptions hiding in those abstractions that we're going to see are problematic. And the question that I'm still grappling with, and this is very much future work, is what are these assumptions that are reasonable? And for the ones that are not reasonable, that we can't seem to shore up and get to be true enough in practice for our purposes, then what are the alternatives that we can design a different foundation of algorithms from? And the way that you usually encounter this as a student is an algorithm is taught to you as something like a recipe, right? It's a sequence of steps, and if you follow the steps, then it should perform an intended function from inputs to outputs. So the idea is that there's a many-to-one mapping from algorithms to functions. There are many potential algorithms that compute the same function. And an algorithm is sort of a specification that we imagine sort of runs in this ideal kind of world, like a recipe, right? We imagine all the equipment is going to work the way we think it will. We imagine the person doing the recipe is going to follow our instructions perfectly, and then nothing is possibly going to go wrong. And when we choose from that many-to-one mapping of algorithms to functions, we have a few criteria that we look at in making that choice. We look at things like correctness. Are we always computing the right function on every single point in the input space? We look at things like running time. How many individual instructions are we going to execute? What kind of instructions? What kind of memory usage does the algorithm require? What kind of equipment? Can it be done in parallel? Or does it have to be sequential? Can it be done in a distributed way, or does it have to be centralized? And what is its robustness to error? Although we mostly focus on this at the testing phase or in the distributed setting. We haven't so much focused on this in the sort of design of algorithms that are going to function on one machine at a time. And in our testing regime, we tend to think about things like coverage of the testing suite, like does the code give the right answer on average cases? Does the code give the right answer on edge cases? What's its running time in average case versus worst case, and what is its memory usage, et cetera? And we think about an ideal test suite as something that can find any incorrect function evaluations, no matter how rare they might occur in practice, right? So an ideal test suite is something that can test all the possible inputs that the algorithm might run over. But what we're really neglecting here in this design of testing is the algorithm's environment. So the environment we imagine when things go wrong looks a little bit more like this. We sort of imagine that we're still in this kind of kitchen where things are going to follow along the recipe, but we might have some deviation from that. We might have some events that occur, but we still think of ourselves as sort of the designer as being in control for the most part, and then sort of responding on an ad hoc basis to these problems that arise. But in malicious environments, we're sort of not even the cook in the kitchen. We're sort of more like the mouse who's facing a maliciously designed trap, not a sort of benign aberration from normal behavior. And so just to highlight some of the assumptions that we implicitly make when we think about algorithms in the design phase that go awry when we actually put them into practice, we typically assume that external inputs are going to conform to our expectations, or that good code is only going to produce good outcomes, that it's going to run in isolation without anything else happening on the processor at the time. And we usually imagine that it's going to run sequentially, that if we write down a sequence of steps, that they're going to be executed literally in that order. So all of these get violated quite often. So to give you a sort of different paradigm for thinking about these things instead of the recipe paradigm, I want to suggest that algorithms are really more like people than they are like recipes. They get interrupted, they get quoted out of context, and they're constantly under surveillance. And so just to be clear, I'm not talking about algorithms as trying to imitate people, or the artificial intelligence kind of view as algorithms eventually acting like people. I'm more suggesting that algorithms are currently suffering from a lot of the failure modes that people suffer from in their daily lives. And so let me start with on interruption. So usually when a program pauses to take user input, we imagine that the user is going to follow sort of conventions for how that's going to look like. So if we're writing into a database, for example, and we ask someone to input a username, sort of imagine they will put in something that plausibly fits as a username. But what happens when somebody violates these conventions. So we might give them instructions, say enter a username with 3 letters and 2 numbers, and they might give us back something else. Now, why would somebody do this? Well, they might be trying to inject some kind of malicious code or other corrupt data into our system. And so if we don't also check in our processing of this input, if we just sort of blindly write it into our memory, then we could have just overwritten other things that were core to the operation of the program and what we're trying to do. So any expectations we have for user input, like that a username is always going to be something containing 3 letters and 2 numbers, needs to be very explicitly forced and checked at the point that this untrusted user input first interacts with our system. So we need to sort of take a little piece of code like this and wrap it with mechanisms to enforce this condition that we're implicitly assuming the user is going to follow. And so this kind of error is pretty widespread and has led to things called buffer overflow and SQL injection attacks. And it really follows from this paradigm we have in our mind that data and code are different things. So we think about data as living separate and being a separate kind of object from code, but in computers, they're really all the same kind of thing. And so something that when we ask for data and we start writing it into memory, it can become code despite the fact that that's not our intention. And because the way these things look inside the actual memory is that instructions are sort of stored in the computer the same as data, and we have something called the instruction pointer that controls which instruction is next to be fetched from the piece of code. And so this instruction pointer itself, it is a pointer, it is stored in memory. If someone could overwrite that with something else, then they could take control of what the program is doing and which instruction the program is going to fetch next. So we really need to be careful about this separation we have in our minds between data and code, because if I can just make this instruction pointer point at something that is user-entered data, I'm now allowing users to execute code on my system. And I've violated that sort of core separation that I wanted to be there. And there's a natural fix to this, which is very tempting from a human perspective, of just, okay, well, if we like this assumption of data being separate from code, let's just enforce it. Let's have dedicated fixed memory portions for writing data versus executable code. And so this is something you've seen in processors from time to time, this setting of sort of write or XOR execute. So what that means is that literally each little spot in memory is assigned to either be data that can be read or written but not executed, or assigned to be code, and you can sort of control now that the instruction pointer only ever fetches instructions from the code side of the fence. And so this seems to be a way of enforcing our implicit assumption that data and code would be separate. It's hard to live with in many contexts, essentially, especially websites, where people have come to expect the flexibility of being able to execute code from untrusted sources that you wouldn't want to write into this privileged part of memory where the trusted code lives. So every time you're visiting a website, you're seeing other people's code sort of operate on your system, and that would sort of have to go over here because we don't want to mix it with the trusted code of your operating system, which sort of already implicitly violates this kind of divide from a functional standpoint. But also more seriously, the implicit assumption further underlying this defense is often false as well. And this is because even good code can have bad consequences when it's able to be quoted out of context. So an interesting thing that happens here is that bad code can lead to bad behavior. That's true. And that's a sort of motivation for us separating out data from code so that we can only have good code. But it's also true that good code can lead to bad behavior if the control flow is still compromised. And so the human analogy of this is that regular people can be manipulated into doing bad things if the circumstances are right. And so we see this in something called return-oriented programming attacks. So in these kind of attacks, the idea is to exploit snippets of legitimate code to still achieve an unintended consequence that the designers of that code would never have wanted to occur. And this can be done successfully when the control flow is subverted. So if someone gets control of that instruction pointer, even without any injection of actual malicious code. So if you can just take the code base that's there, sort of reorder it, you can still compute pretty arbitrary functions from that code base. And in retrospect, this really isn't that surprising, because when we design code, we have this implicit assumption of order. And if you sort of execute instructions out of order, to sort of rebuild any particular program into almost any other program that you would want, if you just take these very basic building block instruction pieces and reorder them. And so the way that this looks in practice is that you take little snippets of code that end with the return instruction, and because they end with return, you can sort of string them together, and they call these gadgets, and you can build up these little gadgets and recombine them into pretty arbitrary programs on most systems. And so this allows you to sort of write your own malicious code, just completely still inside the legitimate side here of this fence, because you're just reusing bits of legitimate code just in an unintended order. And please stop me with questions as I go along if anybody has questions about anything. And so things get worse from there. We also have code that's heavily under surveillance. And we noticed this quite a while ago in the cryptographic world, that in our imaginations, a secret key sort of locked away in an impenetrable safe. But in reality, of course, it's on a machine. And machines have observable properties, like the time it takes them to do computation, the energy that they use, the noise that they make while they're doing computations, and so on. And what this essentially does is it allows somebody with proximity to the machine to learn some small bits of information about the underlying cryptographic keys that are underneath it, which at first sounds like a spy story kind of scenario, that someone's in the coffee shop next to you, sort of like with a microphone on your laptop, measuring the noise output to try to get your secret keys. So as you can imagine, they had to sort of simulate this in the lab to demonstrate that this was possible. But things like timing-based attacks, now that we have a lot of shared hardware, and we have a lot of other people's code constantly running on our devices through websites and things like that, measuring the time a certain program takes is also related to the time that other programs on that same machine take. So in cloud computing and other contexts where you have a bunch of programs running on the same machine, I can learn something about the resource use of your code that's running on the same machine as my code by observing when does my code get slow, when does it get fast relative to yours, and so on. And so these bits of information linkage start to amplify when we have more sharing of hardware and more sort of shared access to communication channels and these other resources that programs use, especially in the cloud computing environments, the fact that they use the same memory caches, which is a huge determinant of speed and energy and all these other things. And so you get effects that are pretty visible to other programs that are running on those same machines. And cryptographers had some proposed solutions to this. They sort of took this reality that certain bits of information about the keys could leak, and they reappropriated it into security definitions and tried to build crypto systems that satisfied those definitions. And so the idea here is to think about it as something in between a black box and a purely exposed secret key, and instead think about this as there's some interface that the attacker has to learn some limited information about the secret key. And this is a challenging modeling problem because you want to balance two things. You want to limit the attacker's information enough so that we can still have secure crypto systems. If he's just allowed to get the secret key, then there's nothing left for algorithm designers to do. We're not going to be able to design secure crypto systems. But if we make too explicit and specific the limitations on his knowledge about the secret key, then what we'll be doing is designing systems that circumvent one particular line of attack that we know about today, and it won't stand the test of time as more and different attacks are discovered. And so what we've sort of proposed is that we can model the attacker's knowledge of the secret key through these external communication channels as some function of the secret key, and we can limit this function in different kinds of ways. We could limit it to be a certain simple form of a function, so a low complexity kind of function. We could limit it to only output a certain number of bits. So let's say it might only output a few individual bits of the secret key, like 1 out of every 10 or something. So we can try to keep this function class as broad and as flexible as possible while still limiting it in some way, so it obviously should not include the identity function so that we get the full secret key and we can just break the crypto system. But as long as it satisfies some reasonable constraints, either in terms of complexity or in terms of its output size, we can still argue that even in the presence of this additional knowledge about the secret key, this partial knowledge, we can still design secure public key encryption, secure signatures, and all the kind of things we want to do in cryptography. And so what's interesting about this, though, is as mathematicians, when we try to prove something, it's often a little bit too constraining to prove it about the same systems that we had before. So in order to get the sort of proof technology to go through to argue about the security of these systems, we have to change the systems a little bit. And in fact, we know that needs to be the case in some cases, because things like RSA, people have actually shown that if you learn certain partial information about the underlying keys, you can recover the full key and you can break the crypto system. So we know, at least for certain bounds on F, where it still seems plausible that you could have security, some of the systems that were designed before this was a concern do not hold up to that, and we have explicit attacks on them in practice. There's even an attack in practice called the cold boot attack, where you can take somebody's laptop and without even turning it on, you can read the RSA keys off of it, which is pretty cool. And so we know we need to change systems a little bit, but what's somewhat interesting is that if we do that, so we add a little bit more mathematical structure to the systems, we can prove guarantees like the following. So we can prove things like if an attacker learns only, let's say, 100 bits of arbitrary information, so that's where at least we're modeling all sorts of different kinds of attacks, timing attacks and measuring energy output and all those things, as long as the sort of quality of information you get out of it can be contained in, let's say, 100 bits, and you're starting from a 1,000-bit secret key, then we can prove that desired security properties still hold. So you're not going to be able to break the encryption, you're not going to be able to forge signatures, all those kind of things. So this is a little victory for the theoretical cryptography community. One major caveat, the changes we made to the algorithms that allow us to prove this may exacerbate the information leakage in the first place. So we don't have good ways of measuring what properties of algorithms and computation actually lead to this side channel information being measurable, and do these countermeasures that we're putting in to make the proof actually make it more likely that more than that 100 bits of information will be measurable through these external circumstances. Because every time we add computation, every time we add something fancy to the algorithm, it is an additional opportunity for the attacker to collect information. So what we really need here is a more integrated way of measuring both the algorithm and the sort of attacker capabilities in a more integrated way at the same time, so that as we change the algorithm, we can sort of have a more realistic notion of what this is going to do to the attacker capabilities. And we don't currently have a design model that allows us to do that. And so it's very difficult to determine in real life how to set these parameters and how to know what is going to be the real capability of the attacker here, and if this 100 bits of information is going to be enough to capture sort of what the attacker can learn through these side channels. And in particular, people are discovering new sort of side channels all the time. So you may have heard about an exacerbation of this effect that was discovered recently, widespread, in particular on Intel chips, called the meltdown and Spectre attacks. And this was kind of, for cryptographers, this was kind of like a small little niche area of cryptography suddenly going mainstream, because it turns out this doesn't just affect cryptographic keys, this actually affects sort of everything. And the reason this happened was that there was this sort of underlying assumption in code design, even in the security critical code, like protecting the operating system and kernel memory access and things like that, that instructions would execute exactly sequentially. So you have instructions that are security critical that are checking conditions for access. Like, is this user, is this program an administrator access who is allowed to touch this critical portion of the kernel or of memory? And then underneath it, you have, the things that the privileged user is allowed to do. And from a pseudocode design perspective, you would look at this and you would say, as long as that access condition is tightly controlled, let's say as long as you check their credentials, as long as you're authenticating the user properly, this code should be fine, because you will never get to that line unless you've successfully passed the authentication check. But what is actually happening under the hood in chip design these days is that they've gotten so fast and they're trying to gain so many performance benefits that it's too slow for the processor to literally wait to compute each instruction in sequence. Because some instructions take longer to process than other instructions. And in particular, complicated access control checks are probably a thing that takes a long time compared to just grabbing something from memory. So we'll actually start executing ahead, something called speculative execution. And this is a default behavior on all of the chips that we have today. And it will start doing this instruction with the idea that once this instruction completes, if it was wrong about the path that would be taken, then it will revert the effects in the sense that it will not return to the overseeing program the results of these instructions, because it turns out that they shouldn't have been executed. But what that doesn't do is erase all of the interim measurable impacts of that memory being read, which might be things like side channel information, like power, access, timing, and in particular, whether something is in the cache or not. So the way that memory works in these kind of machines is that you have a hierarchy of memory. You have a small amount of memory that's really fast, and then you have a next level memory that's a little bit slower and a little bigger, all the way down to a huge amount of memory that's very slow and very big. And when you execute instructions that read memory, there's a usual pattern of usage where things that tend to get read a lot get put into these super fast and small caches of memory. And so you can manipulate the program to start putting things here that are sensitive into the cache. And then you can determine things about that sensitive memory by running a different program on the same machine that doesn't have this privileged access, but that can observe its own hit or miss rate on the cache to sort of make inferences about what's in this memory. So as soon as you have shared devices sharing the same caches, and as soon as when you're cleaning up the impacts of this, when you're not going and clearing all the caches, which would be a huge efficiency drain, you have these sort of lingering effects of these computation that aren't supposed to be visible to this program that's failing the access check, but nonetheless are physical realities in the system that then can be observed and used to extract critical information. So what we have here is an access control layer that's entirely subverted in spirit by the fact that it can have a physical impact, by the fact that what's below here can have a physical impact on the system without the access control check actually being satisfied. And so we're used to thinking about this in the cryptography space as if you mess this up, if you have some kind of bug at the access layer, then of course you get problems. But even if you do it correctly, if there is some speculative execution happening right under your access control, which are fundamentally will be, this can be exploited to sort of get around access checks. And one thing that is particularly interesting about this is it works extremely universally. It doesn't rely upon any particular bug in code. It does get a little bit tricky to actually exploit because your speculative execution path is going to try to make guesses as to which way the program is going to go. And it does this using sort of machine learning techniques. So it does traces of watching the program run over and over again to try to decide which way is the more likely path. So to actually exploit this, there's sort of a phase where you have to train the branch predictor to think it's going to go the wrong way, and so it's a bit of a complicated exploit. But we never want to sort of be relying on the fact that a statistical model and machine learning are not going to be manipulated into going the wrong way, because the entire idea of statistics is it's an average case behavior. It's meant to be an average case behavior. It's not meant to hold the weight of avoiding these the subversion of these kind of access control checks. The fix to something like this, once it's sort of embedded everywhere, is really tricky, because this was sort of an interface error between hardware designers and software designers. You had software designers thinking that they could write a line like this and it would be sacred, and you had hardware designers thinking, well, as long as I don't actually return the results to the calling program, it's fine, I can violate the order of instructions. And so you have an interface error between those two groups. And in order to change this, essentially what they've had to do is they've had to sort of disable speculative execution where they can to protect critical kernel memory, which is going to be a very significant performance hit on all the chips. And but there's some lingering things in there that they can't disable it for that's going to be with us for a long time. But the interesting question, of course, from a scientific perspective, is how do you avoid this in the future? And how do we sort of make that interface between hardware and software, between software and algorithm designers, and ultimately between algorithm designers and the people making the specifications for what they want out of these systems in the real world? How do we shore up all of those communication surfaces so that any assumptions that we're making are explicit and well understood and don't fall out of sync in these kind of ways, which is a much more interesting human problem. Okay. And so a kind of nuclear option, if we don't want to solve the sort of harder human problem, that's also been suggested by cryptographers in the face of things like this, is something called program obfuscation. And so pretty much for as long as these kind of ideas about code have been around, there's been this idea, well, you know, the problem is that people can actually read and understand code. I think the problem is kind of the opposite, that people can't read and understand code. But if one believes that we could solve the problem by sort of encrypting code and still allowing it to run, then we can sort of allow the adversary to observe all these effects, to sort of play with the code, to do these kind of attacks. And the idea would be that they still wouldn't be able to extract the underlying secrets. The intention being, if there's something like cryptographic keys that are then used for access control, that this can sort of protect you from a wide variety of attacks. And so the idea is something called program obfuscation, which has been studied in practice quite frequently. People have commercial products that try to sort of insert dummy variables and extra loops of computation to obfuscate what's going on. Most of the commercial products you can break relatively quickly. So looking at this from a more formal mathematical perspective, what we're trying to do is we're trying to take a bunch of code that may have bugs in it, that may have exploitable properties in terms of speculative execution. It may have all sorts of features that we don't want to reveal to an adversary. And ultimately, we just want to view it as something that takes inputs and produces outputs. We want to get back closer to that abstraction of code as a function that sort of just takes inputs and produces outputs. And we have an adversary who's watching all the intermediary steps and who can see the instructions of this code. And the goal is to produce a version that behaves more like a black box. So we're concerned that this adversary's view of the code itself, which is sort of an extreme model of the adversary's access to the system as it runs, if we sort of take the extreme view that he can view the code itself and do anything that he wants with the code, then what we'd want is to essentially obfuscate the code so that even watching the code as it operates, even observing all of the intermediary variables and all of the instructions of the code would somehow not give the adversary information to exploit beyond just the behavior of inputs and outputs. Okay, so fundamentally, we need to run the code, so it still is going to be a function from inputs to outputs. So anything you can learn from sort of querying the function table and saying, give me the function at this, give me the function at that, the adversary can learn. But sort of beyond that, the idea is that he shouldn't have any additional information that's not sort of explicitly required by the running of the program. And so, so if we could actually do this, so we could have a way of sort of encrypting code such that it would still operate, it would still compute the function, but would not leak any unnecessary information beyond the inputs and the outputs. So a particular case where this would be interesting is the case of software patching. So if we look at the responses that we've had in industry to these kind of cybersecurity problems, a big concern is being able to update systems. And so the hardware update is an even harder problem. The software update is something we all live with all the time. And sometimes what happens, though, is a practical problem of the update is not shipped out to everyone at the same time. So we don't always agree to restart our computers the first time we're asked. It's a process that's slow-moving across different machines. And so what happens is we can start distributing an update to certain users, and they're going to get it asynchronously in time. And this can cause its own problems, because somebody who's getting the update first might actually read the code of the update and figure out where the vulnerability that's being patched was, which may have been information they didn't know before. So sometimes we're patching because there's an explicit vulnerability that is known to someone, but the patch itself might reveal what the exploit is to a larger group of people, and that person may then go and exploit it on the yet-to-be-patched machines. So by the inherent nature of software patching, that it's a distributed distribution, we can introduce an additional vulnerability for no particular reason by sort of giving this critical information to some users ahead of others. Of course, we can't really avoid this. So the idea was if we can somehow obfuscate the patch, if we can still allow the patch to run, but to make it difficult to reverse engineer from the patch itself what the underlying vulnerability was, that we can avoid at least exacerbating problems in this way. And so something that's being very heavily worked on right now in the research community is how do you take sort of relatively simple software patches and obfuscate them in such a way that they would hide the vulnerabilities. And for pretty simple kinds of code, this is possible. The main drawback of this kind of thing is that whenever we encrypt something, whenever we try to make it more secure, we obviously make it slower. And the more computation you want to protect, the sort of more amplified that efficiency problem becomes. And at least in the current ways that we're considering doing this, mathematically, it's a huge efficiency hit to obfuscate anything. And so we're certainly not anywhere close to a world where we could sort of run all programs this way, nor would we necessarily want to. So it's a very targeted approach that works for limited things like software patching, but really doesn't scale to the extent of protecting us from widespread speculative execution and other kinds of inherent vulnerabilities. Which really, I think, suggests that what we need is a sort of paradigm shift in designing algorithms for these kind of conditions, and especially for testing algorithms for these kind of conditions. So we test algorithms today in extremely controlled environments. We essentially build test suites of inputs so that we're worried about bad inputs. We're sort of allowing the programs to run sort of in isolation on controlled hardware. sort of without user-generated input necessarily. So often we sort of think about testing and choosing between algorithms as well in this sort of very controlled, very prescribed environment. And it needs to be something a lot more broad. It needs to be something where we actually simulate real conditions and the real kind of threats and violations of underlying mechanics that we're going to see in practice. And so I think what we should be moving towards is something more like threat modeling for algorithms. So we do threat modeling now for systems, where we imagine all the different sort of attack surfaces, and we reason about the things that we could do to prevent those attacks from being effective. And so we could do the same thing for algorithms, and it starts with an ability to articulate very clear and specific and narrow security goals. So security goals like that a special part of the memory that holds, kernel access should be inaccessible to someone who doesn't have the sort of requisite accesses, or that secret keys are protected. So we need to sort of identify some reasonable and narrow security goals. We still need modular design so that we can achieve high-level security properties as a consequence of low-level properties. And most importantly, we need to identify and make explicit the assumptions that we're working under at all sort of layers of the design process and the implementation process. And we need to model what happens when these kind of assumptions are violated. And what's interesting is that we often like to think, especially in terms of machine learning and statistics, that rare violations of assumptions lead to mild difficulties and outcomes. So if a machine learning kind of algorithm is wrong 1% of the time, or in 1% of a randomly chosen input space, that's sort of what we design it to do. That's sort of what we expect. But in the cybersecurity kind of domain, even a small violation of an assumption is more of a chaotic system. It can lead to essentially break of the entire system. So what that means is that we need to sort of robustness test our algorithms, not only in the sense of the input space, but in the sense of minor violations of the underlying assumptions. So like minor violations of the order of the statements being executed. We could have modeled that and thought about it ahead of these kind of things, but we sort of relied upon a modular design principle that didn't end up holding in practice. And so I think what would be the right approach to this is something like expanding the testing of correctness of algorithm with differing inputs to testing of security properties in different environments. And this becomes a really fun challenge of designing sort of penetration testing and designing adversarial condition simulation on a broader scale, looking not only at adversarial inputs, but sort of things like speculative execution, things like shared hardware, and so on. This is a great problem to give to students. My students are having a lot of fun right now attacking each other's kind of designs and that sort of thing. And this is another way that we vet designs in cryptography, is that we have open competitions between designs, and designers are very motivated to break each other's things and to break each other's designs and find different vulnerabilities. And it's an interesting challenge, and also from the game theoretic perspective of how to incentivize researchers to go out and study vulnerabilities and find vulnerabilities, because we often get a lot of two kinds of work. We get cryptographers building systems because it's easier to build a system than it is to break a system like AES that's been around for a long time. And so there's a saying, if you want to do cryptography, PhD, you build a system. If you want to fail to get a PhD, you try to break AES, right? Like if you try to break something and it just holds up, then we don't sort of reward people for that in the academic world. So it's a little bit tricky to incentivize this kind of work of simulating adversarial conditions, because the best news that you can get at the end of it is, oh, the algorithm design holds up, and it's difficult to publish a paper. So it's a bit of a challenge that we're having in doing this kind of thing. It is easy to incentivize people in industry going out and finding bugs, because it tends to be useful to them in all sorts of other ways that we don't want to be abdicating our sort of research design space to people who are incentivized by that in the industry space. So this is sort of where we're at in the evolution, I think, of these kind of things. We're going to keep seeing these kind of attacks, and we need to proactively rebuild, I think, our approach to designing these kind of systems theoretically. So I will take questions.
Thank you for your presentation. Do you believe that the blockchain as we know it now will resist to hackers' creativity for a long time?
Sorry, let me make sure I understand your question.
Do you believe that the blockchain principles as we know it now will resist to hackers' creativity for a long time, or is it here for staying, or for long, or is it?
Okay, so the question is about the blockchain. Is it going to remain with us for a long time? I think the economics are much more likely to kill it than the cryptography. So let's say from a cryptographic perspective, things like Bitcoin, the particular hash functions, the particular signature functions they use are perfectly fine choices. We believe I believe there will be secure hash functions for a long time, and it's a pretty modular design. If something like the MD5 break happened for their particular choice and they need to swap it out, it's a flexible technology. They would be able to do that. I think what's interesting from an economic perspective is the initial idea is very exciting, which is to totally decentralize authentication, right? Because if you have sort of trusted parties in a system, you don't need proof of work. So what we're seeing with things like Bitcoin in particular is this idea that I don't want to have to authenticate you to allow you to contribute to my database. I want everybody to be able to do it. The challenge with that is getting around something called Sybil attacks, which is where a single user can control a disproportionate amount of the network. So if you make it too easy to sort of participate in an open system, then a single botnet or a single person can sort of have an outsized influence. So the intention of the hash function, which I think does work, and it does satisfy this intention, is that I can control how this bar to participation and sort of set it as a mathematical parameter and say, you have to allocate this much computational resources in order to participate in the system, and it's sort of a dial I can turn. That part, I do believe, works. But what's interesting about that is that there can kind of go two ways. Then the question becomes, what is the best, most efficient way to allocate resources towards solving that proof of work? And if it turns out in the long term that the best way is a general purpose machine, like a laptop, then we worry about things like botnets. Because I may have said you have to allocate this much computational energy, but I have a totally separate problem that people have been very bad at solving historically, which is how do I actually control access to the machines in an authenticated way? If I have a case where a single virus can take over 1 million machines and then has that proportionate control in a blockchain network, then I really haven't solved my underlying authentication problem of having it sort of be individual people in a decentralized sense. So it really comes down to one, if you believe the sort of one machine, one vote system is a good idea, is really dependent on how much you believe in the authentication of machines or the supremacy of botnets. Sort of second way that can go which is what is happening now, that the best way to mine Bitcoin or participate in these proof of work systems is a specialized hardware. It's not your laptop. Your laptop is an inefficient way to mine Bitcoin. And what happens then is the people who invest in this specialized hardware, they pay energy bills and they pay other expenses that come at sort of an even rate. And they get Bitcoin rewards that come more sporadically. So the expected value is right, but the sort of returns over time are not smooth. As we know from sort of other economic systems, what happens when returns aren't smooth is people are motivated to pool together to sort of smooth out their return curve, and we get mining pools, which is what we have now, that people are mining together and splitting the rewards. And at this point, we have a handful of mining pools that control more than 51% of the network, at which point you've sort of reinvented the corporation to some extent. So I think the underlying hash function, the idea that you can set a difficulty parameter, sure, that totally will stand the test of time. whether blockchain systems actually solve any of the higher level economic and incentive-based problems that they're intended to solve, I'm a lot more skeptical on that front.
I have read from many to one, and the reverse will be from one to many. But that is my real question. We can also have from few to few. Yes, but the real question I want to put for you from the up down, up to down, down to up. At what time can we use one method?
Ah, okay. So the question was, when should we use top-down and bottom-up? I mean, I think it's a natural tendency that we have, whether it's the right way or the wrong way. It's hard to stop ourselves. I think what we do is once we get an underlying piece that makes sense to us, that seems to capture some appealing aspect of the problem or of the world, we sort of naturally then start with that and start building up. And I think what forces us to flip it is when we sort of get to the top and we realize that we're not capturing some important piece of the world or of the problem, and then we sort of go back the other way. So I think in research, obviously, it's ideal if we can be doing both, if we can always be trying the problem sort of both ways to try to find something kind of in the middle. But I think people are very natural system builders, so we like to take small things and build them up. And then when we get to the top, though, we have to reassess and say, what other aspects of the problem or of the environment or of the goals are we not capturing, which then motivates us to build new building blocks at the bottom layer.
Thank you. Maybe one more question.
For program obfuscation, aren't you supposing that you trust the source that distributes the obfuscated program? Because
yes.
If you download a program that is obscure and nobody can authenticate it, then you have another problem.
Yes, absolutely. So the observation was that in something like the software patching example, we are trusting the source of the software update, which really means we're trusting our ability to authenticate the source of the software update, which is kind of a fundamental truth in all of these systems, that all of these fancy problems really come down back to the core of authentication, which is the main challenge of these kind of distributed systems and internet scale kind of systems, is how do I really know who I'm talking to, and how do I really know that that person has the permissions that I'm enforcing, which is where things like blockchain are one kind of approach to that, signatures are one kind of approach to that, and that is its own kind of challenge that is separate from all the rest of this. So this is sort of resting on, pick whatever combination of your favorite authentication methods are, and then what can you do on top of that? But that in and of itself is a hugely interesting question.